Hello again, Physics 30s. In today's lesson, we are going to talk about a theory, that being the quantum field theory, which is going to make absolutely no sense to you. In fact, when I explain it, it's going to seem like it's a fairy tale from like a children's book. Because in order to properly explain quantum field theory, you need a level of mathematics that is like well beyond like what we do at the high school level. I mean, even after all the math that I did when I went through engineering, was still not enough math to like properly understand how this works. But anyways, I'm just going to qualitatively to just describe it. Although again, it's going to seem a little bit like this sounds ridiculous. Okay, no need to state the learning outcomes because they're just the same as the last time. And let's get into a discussion of quantum field theory. Okay, so I'll set up the context of what the theory tries to do. So let's say that we have two charged particles. I have one charged particle, proton here, and I have another charged particle, proton right there. Now, we know from our electric forces and fields unit that like charges repel. So this guy would want to repel towards the left with an electrostatic force, which is Fe. And this one would also want to repel towards in the opposite direction with an electrostatic force. And these two electrostatic forces would be equal and opposite. Okay, so we know that like charges repel.
Could someone from the facilities team please go to the band room to let a student in for an instrument?
Sorry about that. But why? Why do like charges repel? Why do opposite charges attract? So the quantum field theory attempts to explain like why is this law true? Why do like charges repel? And here's how it explains it. Quantum field theory tells us that mediating particles are the mechanism by which the fundamental forces act over the distance between particles. Okay, so this is essentially what it's trying to tell me. So why do these two guys repel? Okay, in between these two guys, there's a mediator, kind of like a mediating particle. So I'm just going to draw a circle just to represent it. Okay, so we'll call this the mediator. What this mediator does is it goes to this one and it tells it, hey, you need to repel, go towards the left. After it does that, it then goes back to this one and says, hey, you need to repel, go towards the right. And then it just keeps going back and forth, telling these guys they need to repel and telling them what force to repel with. Okay, this sounds absurd because I'm associating sentience with like the mediating particle when it actually doesn't have that. But in a nutshell, qualitatively, that's what's happening. So like, why do they repel? Because there's a mediating particle that's constantly going in between them that's telling them they need to do this. Okay, don't worry about that diagram. It's not important. Not at a physics 30 level. Okay, so you might be like, okay, cool, I guess. So there's a mediating particle, but that sounds a bit fishy. So why don't we prove that it exists? Like if we can prove the mediating particle exists and it's constantly going in between these two charges, then I might buy this story. Well, you can't. So this mediating particle is what we call a virtual particle. The reason it is a virtual particle is because we can't actually detect it. It cannot be directly detected by a particle accelerator. It constantly goes in between these two charges, but there's no way for us to actually prove it, like experimentally. However, mathematically, involving a lot of really complex models and a lot of like really awful math, the theory is supported. And again, that's why it's called a theory. Like a theory isn't necessarily this is exactly what's happening. It's just an attempt to like explain like some kind of phenomenon. Okay. And usually like later on theories are contradicted and we replace them with updated ones. We went through this entire exercise with our model of the atom, but it is just a theory. And again, I'm really like making fun or poking fun at like how absurd the theory is, but with the proper mathematics, you would have more of an appreciation for it. Okay, now what we want to focus on is we want to focus on these fundamental forces. So what are our fundamental forces? And for each fundamental force, we're going to talk about what is the mediating particle that's making all these interactions happen. So let's start off with the gravitational force. And let's summarize everything we know about a gravitational force. A gravitational force is always a force of attraction between matter. Okay, between any two masses, they always want to pull them, they always want to pull together. Two, the gravitational force has an unlimited range. If you look at the equation for calculating the gravitational force, that's Newton's universal law of gravitation. So Fg is equal to capital G m1, m2 over r squared. There's no restriction on how far the particles can be apart, except for it can't be zero. The particles can't be sitting on top of each other. So what we can see is there's an inverse square relationship between Fg and r, which means like as the particles get further apart, the force gets a lot weaker. In comparison to the other forces we're going to talk about, it is hands down the weakest force. The only time the gravitational force is like even remotely significant is when we're talking about an object that has a humongous mass, like a planet. Otherwise, if like you looked at the gravitational force between you and a stapler in the room, it's so ridiculously small, you may as well just ignore it. The mediating particle, okay, so what's the particle that tells two masses, hey, you guys need to attract and come together, is called a graviton. Now, there's a bit of a problem with the graviton. So not only can we not detect the presence of a graviton because it's a virtual mediating particle, we have never in any other scenario outside of like looking at mediating particles ever seen a graviton or proven its existence. So its existence is only proven mathematically. And again, if you go through the math of the quantum field theory, I'm sure you'd have the proper appreciation for it. But it's just, again, it's a little bit sketchy because like A, I'm asking you to buy there's mediating particles. And then two, I'm telling you we can't detect them. And then three, I'm telling you the mediating particle for a gravitational force is a particle that we've never under any other circumstance have observed. Okay, but the theory does support it mathematically. Two, let's go to the electromagnetic force, our second fundamental force. Electromagnetic, it could be another word for your electrostatic force. We just call it electromagnetic because there is a connection, as you know, between electricity and magnetism. So what do we know about this force? One, it can either be attractive or repulsive. So if you have like charges, they attract, or so like charges, they repel. If you have opposite charges, they attract. Two, just like the gravitational force, it also has an unlimited range. So you can use Coulomb's law to calculate the electrostatic force or electromagnetic force. So Fg is kq1 q2 over r squared. And again, we have no restriction on what the range can be. Just the force gets weaker as the charged objects get further and further apart. The electromagnetic force is a lot stronger than the gravitational force. Well, in a certain context. In the context of looking at hydrogen, where you have a proton and just an electron moving in orbit around hydrogen, the electrostatic force between the electron and the proton is way, way larger than the gravitational force. In fact, the gravitational force, you may as well just ignore it. It's so ridiculously small compared to the electrostatic one. Again, that gravitational force only is a big deal when we're talking about humongous objects. Okay, what's my mediating particle? The thing that's telling the charges whether they should repel or attract? It's a photon. Okay, well that's good because we at least have evidence that photons exist. So at least this mediator is something that we've observed like elsewhere. Three, we have the strong nuclear force, which I've made a lot of references to in the first part of this unit. Okay, so now let's talk more about this. Let's describe it in more detail. So what is a strong nuclear force? It's the force that holds the nucleus together. So again, if you look at an actual nucleus, you have a bunch of protons inside the nucleus. They want to repel. They want that nucleus to explode. It's the strong nuclear force that holds the nucleus together, the glue that holds it together. It is a really, really, really strong force, but it only has a tiny range. Now, for smaller atoms, that's great because smaller atoms have small nuclei, in which case the strong nuclear force keeps them really stable and intact. But if you have like a large nucleus, we're talking about something like uranium, where you have like 92 different protons in it, the effective range of the strong nuclear force is not quite enough to hold it together, which is why eventually the atom undergoes radioactive decay because the range is just a little bit too short. What's the mediating particle? A gluon. You get it? Because it's a mediator that helps keep the protons and neutrons glued together in the nucleus. Yes, physicists have a sense of humor, although a very, very poor sense of humor. Well, whoever came up with that name has a pretty lame sense of humor. Although if I had to come up with a name, I probably would have made that same name as well. So that also means I have a lame sense of humor. Okay, the fourth fundamental force is the weak nuclear force. What does the weak nuclear force do? It's responsible for converting protons to neutrons and vice versa. Now, we already talked a little bit about this when we described beta negative and beta positive decay. In beta negative, there was the emission of an electron, beta positive, the emission of a positron, but also there was a conversion between protons and neutrons when we went from our parent to our daughter isotopes. That's what the weak nuclear force does. It has a larger effective range than the strong nuclear force, but it is not unlimited. I would say that like its range is effective enough for something like uranium, which is why it can handle the radioactive decay. So over like a larger distance of my nucleus, it can cause a conversion from protons to neutrons and vice versa. What are your mediators? Okay, well, no lame, clever. I was going to say lame, clever words, or like lame, clever words. But I guess lame and clever doesn't go together. Uh, Okay, you have the W plus particle. That'd be the mediator for W plus for the beta plus decay. W negative would be the mediating particle for the beta negative decay, and you have like a Z0 particle, which is involved in some other kind of radioactive decay that we did not talk about. So we're not going to stress about that one. But we are going to discuss the W plus and W negative particles in the final lesson next time. Okay, now what we're going to do is we have this entire subatomic zoo of particles, and we're now going to look at a classification system for them. So I think this would be like equivalent to, I believe in biology, the classification system is referred to as taxonomy or something. Although I think the classification system in biology is going to be much more complicated than the one I'm going to go through. I once attempted to take a first year biology course dealing with taxonomy because I'm at that point I realized I was going to be a teacher. I'm like, hey, if I teach biology, that would just make me even more like marketable. Like people really want to hire me then. I think I got through like a month of that course, and I'm just like, I can't do it. If it gives me a worse chance to get hired in terms of being a teacher, then like forget it. I do not want to do biology. Not to say that all biology is awful, but I think taxonomy is awful. I mean, a lot of studies of like body systems I think is kind of neat, but yeah, taxonomy is just empirically awful. Okay, anyways, what were we talking about? Oh yeah, taxonomy for physics, these subatomic particles. Okay, so the good news is that the good news before the bad news comes, we can actually group all of our subatomic particles into three families. The first family is the photon family. What particles are in the photon family? Photons. That's it. The way we're going to define these families, though, is we're going to define them by means of the fundamental force, the fundamental forces in which these particles interact. Okay, so I said a photon interacts by means of the electromagnetic force. Well, why does it do that? Well, let's go back here for a second. What's the mediating particle for the electromagnetic force? It's a photon, okay? So if a mediating particle for electromagnetic force is a photon, then we can describe photons as interacting by means of the electromagnetic force because they are the mediator for that type of force. Okay, so that's family one. It has photons of varying frequencies. Family two, we have the hadrons. When I think of hadrons, I think of, again, I possess no memorization techniques. Another reason why I hate biology. When I think of hadrons, I think of hadron and heavy both start with the same letter. So I think of like your heavier subatomic particles. What are the heavier subatomic particles we're talking about? I'm thinking like protons and neutrons. In comparison to the mass of an electron or a neutrino, much larger mass. The hadrons, yes, are heavier particles. It's funny, I wrote that exact same thing directly up there. Heavier particles like protons and neutrons. They interact primarily by means of the strong nuclear force. Okay, so why do they interact by means of the strong nuclear force? Let's go back to our fundamental force, the strong nuclear one. Okay, what does a strong nuclear force do? It's the glue that holds protons and neutrons together. Okay, so the mediating particle for the strong nuclear force is a gluon, and a gluon is responsible for making protons and neutrons interact so that they are held together. Therefore, hadrons interact primarily by means of the strong nuclear force. Third family, we have the leptons. I think leptons and lighter particles both start with the same letter. So when I'm talking about subatomic particles that are lighter in mass, we're looking at electrons and we're also looking at neutrinos. I've said a neutrino is a massless particle, but again, that's just like quote unquote, like they just have a really, really small mass. These ones just simply do not interact by means of the strong nuclear force. So I believe they can interact by means of the other three, but just not the strong one. That's because a strong nuclear force has nothing to do with the outside of the nucleus. It's all about how protons and neutrons within the nucleus interact with each other. Okay, let's come back to this chart now. And let's see if we can make a bit more sense of it. I mean, we can see our different families on here. So on this chart, we have family number one, which is the photon family. What particles are in the photon family? A photon, okay, of varying frequencies. Okay, family number two, we have the leptons. The leptons, there are actually only 6 of them, okay? 6 leptons. We know about 2 of the 6. We don't know about the electron. There's electron neutrino. That's just a neutrino. Sometimes we call it an electron neutrino because it's typically accompanied with an electron in a radioactive decay process. And we have some other ones too. We have a muon neutrino, a tauon, and a tauon neutrino. But again, there are only 6 of these lighter particles. Okay. Then we have family number 3, which is the hadrons. Now we're going to break them into subcategories in a moment. But your hadrons, again, those are your heavier particles. So in this family, we have our, it's not showing it on here, but we have our protons and we have our neutrons. But just to point out the actual rest masses. So if you look at the rest masses in general of like your hadrons in comparison to your leptons, they in general have much larger masses than that of a lepton, with the exception of this guy right here, which is like the tauon, whatever that particle actually is. The hadrons are heavier. Oh wait, there's a proton and a neutron. They're right here. Proton, neutron. Okay, so that's my 3 families. But we're also going to talk about those two subfamilies there, the ones that's called a meson and a baryon. To distinguish those two families, we need to talk very briefly about another, I'm going to call it a quantum property that's referred to as spin. Spin is a quantum property that resembles rotational angular momentum that is also used to group particles. Okay, trying to understand what spin is really difficult. This is probably better explained by a chemistry teacher than by me. Uh, the best analogy I've ever seen to explain spin, and this is not a perfect analogy, was from a book called A Brief History of Time by Stephen Hawking. And what he used in this to try to explain the concept of spin was he liked to make reference to a deck of cards. So let's go through a little bit of an explanation as to how spin works. Okay, if you have a particle that has a spin of zero, a spin of zero means that if you take that particle and you rotate it by any angle, that particle will always appear the same. So if you have like a dot on a piece of paper and you took that dot and you rotate it by 45 degrees or 90 degrees or like 180 degrees, it's always going to look like the same dot. Okay, so spin of zero just means it doesn't matter what angle you rotate it by, it's going to appear the same. Okay, now I have an ace of clubs from a deck of cards. Now for this one, what angle would you need to rotate this card by so you can get back to this exact same orientation? Well, to get back to the exact same orientation, you'd have to rotate this card by 360 degrees. If you did 180, the card would be inverted, or not the card inverted, the club itself would be inverted. So you need to go 360 to actually get back to the original orientation. And that's what we call a spin of one. So a spin of zero means you take your particle and you rotate it. There's no difference in how it appears. A spin of one would mean you need to rotate the particle completely by 360 degrees to get back to original orientation. How about a 10 of diamonds? What angle would you need to rotate that one by to get to the original orientation? Well, this one actually has more symmetry to it because the diamond has symmetry both horizontally and vertically. So this card, you only need to rotate by 180 degrees to actually get back to the original orientation. So maybe like a rough rule we could use here is we could say that, what's my spin number? So your spin number would be equal to, or how do we want to do this? No, let's change it a little bit. I'm not going to define it in terms of spin number. Okay, so what's the angle we need to rotate it by? So your angle, to get back to your original orientation, I believe would be 360 divided by the spin number. Let's look at the first one. 360 divided by 0 is technically like, I suppose, infinite, if you want to think of it like that. So any combination of angle rotations will result in you having the particle back in its original orientation. Spin of 1, 360 divided by 1 gives you an angle of 360. You got to rotate it by 360 to get back to the original orientation. Spin of 2, 360 divided by 2 is 180 degrees. Okay, this doesn't seem too bad. Okay, this concept of spin. We're just talking about like rotating particles back to the original orientation. Okay, let's go back to this chart for a second and look at some of these spin numbers. Okay, so spin of 1, great. Spin of 0, great. Spin of what? 1/2? Okay, what would that be then? Okay, so if I figure out what angle I'd have to rotate an object by to get a spin of 1/2, your angle would be 360 divided by 1/2 is 0.5, which would be 720 degrees. How does that make any sense? So that means you have to take your particle and you have to rotate it 2 revolutions for it to go back to its original orientation. So yeah, there's probably a little bit of a limitation in terms of how to interpret like spins. I don't think the card analogy perfectly works then, but it works nicely for at least a spin of 0, 1, and 2. Otherwise, it's just some kind of like really weird quantum property that has something to do with like rotating like an object, but we're not going to define it any more than that. However, we're going to use the spin number to look at these other two families here, these subfamilies. Okay, so we have our fermions. Fermions are particles that have a half integer spin. Fermions include both leptons and they include the baryons. So if we go back here, let's just pick a different color. Okay, so fermions have a spin of 1/2. Okay, so my leptons have a spin of 1/2, and my hadrons, specifically the baryons, have a spin of 1/2. So what exactly is a baryon? A baryon is a hadron, with a spin of 1/2. So baryon is, let's use a different color. Hadron with spin of 1/2. How about bosons? Bosons are particles that have an integer spin to them. So that includes all of your mediating particles. Your mediating particles would be a photon, it would be a gluon, the theoretical graviton, W plus particle, W minus particle, the Z0 particle, and a meson. Okay, so what's a meson? So let's go back here now. So photon is a mediating particle, so that would fall into the category of being a boson, B. And a meson is just a hadron that has an integer spin to it. So this would also fall into the category of being a boson. Okay, so meson would be hadron with an integer spin. Okay, so yeah, the classification is getting a little bit confusing, but in the next lesson, we're actually going to come back and define hadrons and leptons a little bit differently. Okay, so you can now finish the particle physics hand-in assignment, and then again in the next lesson, we're going to wrap up the course by talking about quarks, and I will talk to you in that lesson.